Hello, everyone, and welcome to a new Morocco HPC webinar. We are very happy to be back with an exciting and interesting talk. So, for those of you who do not really know about us, we are Morocco HPC and we are very passionate about gathering a vibrant, excuse me, just had to mute it. Yeah, so we are actually very passionate about gathering a vibrant community around high-performance computing in and from Morocco. So our goal is to connect researchers, engineers, and tech enthusiasts to global innovations in HPC. And today is no exception. So we are absolutely happy to welcome an inspiring speaker who stands at the intersection of AI, education, entrepreneurship, and impact, Dr. Sarah Al-Atif. So Dr. Al-Atif is an assistant professor in big data and artificial intelligence, a certified business coach, an AI startup advisor, and a recognized Google developer expert in AI. She is also an instructor with the NVIDIA Deep Learning Institute, a powerhouse for knowledge and experience, to say the least. So, tonight, she will guide us through an incredibly timely and fascinating topic from simulation to prediction, how HPC powers the future of AI. So, from accelerating research to enabling cutting edge AI models, HPC is shaping what is next. And this talk will take us on a journey through this transformation. So, sit back, engage, and feel free to drop your questions in the chat as we go. Dr. Sarah will take them at the end of the talk. So let's get started. Dr. Latif, the floor is yours.
Thank you. Thank you for the warm welcome. Okay, let me just get these slides on. Cool. I hope you can see them.
Yeah.
All right. So I was already introduced. We're not going to repeat these things, right? Let's get directly to the introduction. So before that, I just want to say that when it comes to today, when it comes like what I'm going to talk about, I'm going to mainly talk about what AI is, what HPC is, how AI can help HPC, and how HPC can help us accelerate AI as well. So we can kind of like understand how AI and HPC intersect and how we can better leverage both of these to accelerate both of them at the same time. And obviously solve really tough challenges that we're facing, from climate change to kind of like medical sciences. So first things first, what is artificial intelligence, right? So artificial intelligence is like a set of techniques. It's the whole huge domain that aims to make machines think and act like humans. Artificial intelligence, as the big field, has some let's call them subfields, right? So we have machine learning and deep learning. So for machine learning, at first, when we came out with this kind of like algorithms when it comes to AI, they were just kind of like trying to replicate human expertise, right? So we kind of like, let's say, for example, we go to a doctor or, for example, lawyer, try to understand how they do their job and try to actually code these kind of things. Not in a way where we're using if and else, but more like we're using some kind of other set of predicates. So the kind of like knowledge is built up from the ground up. And if there are some kind of logical intersections or things we can build on, we can actually have these programmed into the machine. Later on, we figured out actually it wasn't really very optimized, right? Because we had to code everything, and usually expertise is not really something that is very easy to translate, even for a human to another human, mind you, to an actual machine that needs things that are actually logical and based on science. That's why they actually kind of like thought, how about we introduce statistics and probability inside these kind of systems? And that's actually what machine learning does. So machine learning is based 1000% on statistics and probability, actually advanced statistics and probability, to kind of like try to understand how the data is shaped so we can model it and then come up with an actual function that we can reuse to do the predictions or anything that we want to replicate. But then, even with these, we were still in a tough spot. We still had, as humans, to interact with the machine and tell the machine what is important and what is not when it comes to the data it needs to model. That's how actually they thought of the deep learning part, where actually for deep learning, they kind of like try to, get inspired from our brains and how they actually transfer information, interpret it. And that's why we have here what we call neural networks. But actually in our brain, we have what we call synapse. And each synapse, you can think of them like, kind of like receptors that transfer information between each other using obviously electricity. So this is a kind of like what we can think of the deep learning part as well. So in here, we do not have, like, as humans, we do not need to tell the machine what it needs to pay specific attention to, so it can actually replicate what's happening in reality. We just need to give it the different data for training and the labels in case we have them. Otherwise, we're doing another set of learning algorithms to actually kind of like give the machine some idea of the things that it needs to do, and then it will try to figure out the rules to do the same thing, obviously depending on its own calculations, without us getting involved in the process. In other words, what is really AI? More specifically, not the old days AI, but the new actual AI, right? This current AI in AI's era, right? So actually artificial intelligence, still the goal is still the same. We're trying to simulate human intelligence using machines, enabling them more specifically to think and act like humans. This is really important. It doesn't only need to process information as humans, but we also need it to act like humans. We need it, feel compassion, share emotions, and all of that. So these systems are capable, obviously, of what we're capable of so far: learning, reasoning, and then problem solving, as well as understanding natural language. That's actually what we have with LLMs when you're writing a request or a prompt, and then perceiving their environment. That is actually what we have with agents. So for example, when they're collecting data from either sensors or just APIs to kind of like understand the information they need to retrieve from you and obviously answer your requests. So what are AI strengths? So AI systems are known for their adaptability. This is actually one of the biggest, kind of like, if we want to think about the biggest gifts of humans, is actually adaptability. One of the things actually we also are very well known for, that is learning and improving from experience, right? So we learn as we go, and then we have automation. So automating complex tasks, that especially here we're obviously talking about things that we already know how to do. It's just, let's say, we need it at a larger scale. And then excellent pattern recognition for predictions based on large data sets. That is just like kind of like figuring out what is repeatable so we can actually get to the automation part. So what are AI programs capable of? So before we were talking about systems, but now let's talk about the programs. So they're actually quite good at identifying patterns, same thing as here, excellent pattern recognition. They're also good at learning and then drawing conclusions. That is obviously synthesis. Like if you give them a bunch of data, they can tell you what's in the data and give you a conclusion or synthesis around it. Now let's get into the high-performance computing systems. So for people who are doing AI and have no idea what high-performance compute involves, so it's actually kind of like, like in AI, what we have usually is that we have a lot of GPUs, obviously in a cloud, or sometimes, hopefully not, CPUs, and the best obviously is TPUs. So all of these are actually just small components, right? High-performance computing systems have all of these things installed into a couple of racks, right, together, and then obviously that communicate between each other to solve complex computational tasks. So what do we really do in AI after all? The only thing we do in AI, technically speaking, all of AI is just matrix multiplication, right? And then tensors. So it's a bunch of multiplications. So it's all math, right? So this is actually what high-performance computing does as well. It solves complex computational problems, obviously, by accelerating the math calculations. So it leverages multiple processors to do so, and vast amounts of memory, obviously, to perform calculations at incredibly high speeds. So HPC is fundamentally considered hardware. And anyone working on AI would know that this is actually what we need. We need accelerated hardware, and this is why we do not only think of actually leveraging high-performance computing systems, but also quantum computing, right? So what are the key components and characteristics of these HPC systems? So the first thing is obviously is supercomputers, right? So what are supercomputers? They are highly specialized and powerful computing systems specifically designed for intensive computational tasks. They're capable of processing complex data sets in record time. Let's say, for example, for us, like for example, the least we can use to get to, kind of like a good AI running up and running, that will be 4 GPUs, right? So these people know they're not talking about 4 GPUs. They might actually be talking about 100, 1,000, 10,000 GPUs together in a huge computer like this one. Okay, so what else? Clusters. Obviously, when we're talking about lots of computing, that means that we will be having clusters, right? Each one will be actually kind of like performing a specific task, so we can kind of like so we can leverage the dynamicity of these systems. So for example, a cluster can obviously contain kind of like, for example, here, laptop internet that gets obviously logged in to these different tracks. So they are worker/computer nodes that perform analysis and compile large packages. So in simple words, kind of like if you're familiar with big data, usually, for example, when we have big data, the thing that how we handle it is that we kind of like get it and then split it into several nodes, right? So we can accelerate computing. That's actually what a cluster is. And anyway, in big data, that's actually what we have. We also have clusters as well. So HPC systems are typically organized into networks of interconnected computers. That's actually what clusters mean, that work together to perform complex calculations. And these connections are optimized to ensure the clusters operate quickly and in sync, obviously, because if we lose one data point, we might lose the whole thing, right? And this is obviously also important for us in machine learning when we're training models in different kind of like clusters, let's say, and we want to gather the final prediction. We kind of like need to make sure that we do not lose the information, because losing just one information actually makes us lose the right prediction. Parallel processing, obviously, when we're talking about having a lot of machines working together, obviously we're going to be talking about splitting tasks, and each one obviously will need to optimize for that task. So parallel processing is a technique where multiple compute resources are used simultaneously to solve a computational problem. Cool. Now, obviously, so with all of these things come what we call density and infrastructure. So HPC computers have a significantly increased number and density of components. So they have CPUs, they have RAMs, they have storage, they have cooling, obviously, to be able to keep these machines up and running, and obviously so that we do not kind of like lose them along the way, because it's very easy actually to lose and actually even burn all of these systems up together if we do not have the right way to manage them and keep them keep them safe, let's say, from any kind of damage. So so they support actually their power, obviously, supply and cooling systems are considerably increased. That's why we have what we call density and infrastructure. That's why it's extremely important that we actually choose very wisely where we put in these all of these materials and equipment, obviously cooling, and then kind of like how are they going to communicate together, what type of other kind of like tools we can use so that we can improve the communication between them. Anyway, there's a lot of headache. Oh, sorry. So how AI can help HPC workflows, right? So actually, like, it's very simple. Anything actually involved in HPC, we can use AI to accelerate it. That's actually what all of these words here mean, but let's just kind of like go through each one of them. So we can accelerate simulations, right? So usually what do we do? What are HPCs traditionally used for? Because now they're used for other things, right? So traditionally, they were used, obviously, to do huge calculations, especially when it comes to the physics, or kind of like any physics parts, actually, mostly. Obviously, you will be hearing about them mostly in climate-related issues. But yeah, that's actually where we're using HPCs most of the time. So obviously, in physics, what do we have? We have a lot of simulations, right? So I don't know. We need to simulate how Earth is actually rotating around the wall system, right? So all of these things require a lot of huge amounts of data. So it's a lot of huge amounts of data, and the problem is that it needs to be reactive in real time. We need to actually visualize what is happening inside Earth, for example, in real time, right? So that's why we are kind of like drawing, obviously, visuals, and they need to be accurate at the time t that you're requesting it to be at, right? So this is actually why we call them simulations, and this is actually how AI can help. So AI can actually accelerate these simulations, kind of how it helps actually accelerate how we can get imaging from MRIs. So if I'm not sure if you know about this, but like MRIs, the one that actually kind of like give us the best medical images you can get, because it can look into all organs related that is obviously looking at. So before, it was really hard for us to get accurate images from these machines, because obviously they're just kind of like drawing a couple of like light, like where is the light really kind of like reflecting on. And because we humans, we kind of like cannot stand staying in one position for a very long time, most of the time they didn't really get accurate images. So what they did is that they kind of like used the AI to infer, that is, let's say, for example, the heart is shaping already. We can kind of like already get the shape of the heart, and the most important regions are already covered. So the AI kind of like complements what is left. So this is actually like one of the things that we usually do, for example, in medicine. So you can think of it like this with HPCs as well. So AI can help them kind of like replace time-consuming parts of a simulation and make them much faster by actually kind of like inferring what is missing or what might already be there based on the data that it has collected so far. So this also includes reduced odds or modeling to kind of like simplify complex systems without losing accuracy, which enables quicker design space exploration. So it can also be used to optimize HPC system performance and operations, which we call AI ops. So AI simulates HPC operations through intelligent resource scheduling. Let's say, for example, I don't know. Today we're having, I don't know, we're maintaining some systems, right? So we do not really need that much. We do not need to use all of our HPC's capability. We only need, I don't know, rack one, let's say the first 10 kind of like machines operating. So for example, AI will figure out that we're not going to be using all of these resources because the actual job that we're launching in this HPC does not require all of those resources. So for example, it's not us that are going to say we're only going to use 10 machines. No, it's the AI that is going to figure out that we only need 10 machines based on the job or the work we're requesting the HPC to do, and then only allocate this kind of like resources to us. So yeah, this also enables predictive maintenance by anticipating hardware failures. So for example, if I don't know, let's say for example, some kind of machine or one rack has kind of like known some issues, it for example, based on the failure productivity, it would know that, for example, that rack wouldn't be able to handle that kind of job. Let's say, for example, it only has CPUs but not GPUs. So it would know which kind of like hardware to choose for which kind of like job that we're obviously requesting from it. So it performs also of auto-tuning and optimization of applications and system configurations for peak performance. So enhancing data analysis and post-processing. So AI helps by automating, for example, feature extraction and pattern recognition from large simulation data sets, identifying important threats and anomalies. And you will see this a lot when it comes to satellite imagery and any kind of like, for example, especially for climate change, they usually use that a lot. So additionally, intelligent visualization tools powered by AI make complex multidimensional results easier to understand and explore. That is 4D, 3D, and anything kind of like complex. As you can see here, this is kind of like retrieved from a paper. I actually forgot to add the source. Anyway, I should go back and add it. Anyway, this just actually shows how actually HPC has grown with the introduction of the, kind of like the advancements of computational power and the different, obviously, kind of like advances in technology, like AI, for example. You can see that we have kind of like we have increased speed, automation, and scale with obviously the different developments, obviously with AI kind of like being involved. It has really helped us increase the kind of like speed and automation and scale. This is actually just a diagram of all the areas where kind of like AI can help with in HPC. So for example, it can help in system optimization operations, for example, with intelligent resource scheduling, like we talked about before, auto tuning and optimization, obviously monitoring, predictive maintenance, like what is going to fail, where, when to expect it to fail, and then optimize system performance. Also, it can help at the simulation acceleration level, where it can reduce order modeling, surrogate models, and physics-informed neural networks. So, for example, instead of using just the typical, let's say, physical kind of like laws, we can obviously use neural networks, AI obviously based models, to improve this physical calculation, these physics calculations. Obviously, this will help us get accelerated simulation results. So also at the data analysis and post-processing level, so instead of, I don't know, taking, for example, instead of us taking, let's say, 1 month to process satellite imagery data, we could take only 1 week if we know what type of imagery we need to focus on, where exactly in the image we need to focus, and obviously all of these kind of things. So yeah. So now the question is, how can HPC help AI development? So once again, as you already know, with AI, we need obviously high performance computing. That means anything that can help us reduce the time to train our models from 1 month to, hopefully 1 day, or even actually 1 hour, we're always up for it, right? So actually HPC, that's what it really helps us with. Actually, some research, and even researchers have shown, obviously they did experiments that actually, for example, what used to take us, like using, let's say, for example, a cloud with 4 GPUs, 5 GPUs, or even A100s, or even actually much bigger of the actual computational powers that are actually extremely expensive, because like the more you're introducing computational power, you're actually introducing material that is obviously very hard to get from nature, so because they are very rare. So this means that we need more of this, and if we need more of this, so we can accelerate calculations or even train LLMs that, or the current ChatGPT or DeepSeek or Gemini, for example, it obviously consumes a lot of resources, not just money, but also resources that we need, and obviously even produces harmful substances to, for example, that actually accelerates climate change, obviously, and make it worse. So here comes HPC, because of its obviously a really elaborate way of accelerating physics, kind of like computation, kind of like obviously solving complex problems, is, for example, based on physics and all the mathematical laws. So actually we can leverage these along with the things that we already know. Usually, like, for example, we can include AI to accelerate obviously HPC systems working, and then we can use HPC to accelerate AI training using less actually amount of power and even less computational resources than we actually are used to do with the current simple cloud computing kind of like ways. So exactly what does that mean? So it actually helps us enable large-scale model training. So HPC provides the massive parallel compute power, as we have already seen, is one of its components, especially with interconnected GPUs. Usually for GPUs in cloud, they are kind of interconnected, but you kind of like sometimes need to actually do the actual connection yourself. That is, for example, if you're going to split the model to be trained on different GPUs, you would actually need to figure out what goes where. But with HPC, because it is already kind of like developed like that, to obviously do parallel processing, so you do not need to figure it out by your own. It's actually the HPC that will be doing the job for you, because it has already been programmed to do so. So obviously this helps us reduce training time from months to hours/days, and the high-speed network fabrics like InfiniBand ensure efficient communication for distributed training across thousands of accelerators. This is one of the problems that we have when it comes to AI, around when we are splitting the data and training the different parts on different GPUs in a parallel processing way. When we actually gather all of data together, we lose the actual accuracy because we do not get the exact kind of like the exact output that we were obviously training for. But HPC helps us actually remove this kind of errors. Obviously also improve our accuracy and the performance of these models. So handling petascale data. So HPC systems excel at efficiently ingesting, storing, and preprocessing petabytes of data required for AI training, and offer high-speed I/O, or obviously input and output, to feed this vast data to accelerators without bottlenecks. That's normal because they have actually been designed initially to handle big data. So it's actually much easier for them to handle this kind of like ingesting, storing, and preprocessing lots of amounts of data. So facilitating complex AI research and development, obviously, by actually it enables hyperparameter optimization at scale. So usually one of the things we do in AI to kind of improve our model's performance is to kind of find the best hyperparameters, right? So that means we have a function, let's say, for example, a multiplied by x power 3 plus b multiplied by x power 2. So we need to figure out the best a and the best b, so we can get kind of to the best results and performance of the model. That's actually what we call hyperparameter optimization. So we need to try different parameters, different let's call them assumptions, so we can get to the right performance. And that takes a lot of time, obviously, and needs a lot of resources, because we need to split these trainings so we can obviously accelerate the process. So it supports model ensemble training for robust AI. What actually means is that usually one of the ways we actually improve performance, again, is actually by having different models kind of doing the same task, and then we kind of for example, fuse their prediction together, so we can get kind of like voting. It's like when you have different humans collaborating together, each human will give you their opinion, and then whoever's opinion is obviously kind of repeating, we're going to get that opinion, right? Kind of like democracy, but obviously we have different ways to do it, and I'm just giving you an example. So, and allows for large-scale reinforcement learning simulations for training intelligent agents. So this is actually really important for obviously agents. So deploying and serving AI models, inference at scale. So instead of actually having to use 4 GPUs or 2 GPUs, so we can do inference. Inference is like the actual prediction, where the model has already trained, and now we're actually expecting the model to do the job we trained it for. Usually we do not need the same resources as for training, but we still need to get more resources if we want the user to get their answer as quick as possible. Obviously, this is extremely important, as you know, we humans do have very low passions. That's why we are talking here about high throughput and low latency inference. That means it can handle a lot of data coming into the model, and obviously kind of you need to wait very little to get your actual answer out of the AI, which isn't really the case if you do not have good computational power. If you have ever tried to install any of the LLMs locally, you would know that if you do not have a highly performant laptop, you might actually have to wait 10 minutes so you can get an actual answer out of these LLMs. So that's why we really, that's what we can call it inference. And this is why we need more high performance computing. So actually we can reduce that time from 10 minutes, for example, to 1 second and 2 seconds. So this is actually the workflow where HPC can help AI. So the main need is that obviously we need for advanced AI capability and AI development stages. So HPC can help us in model training, data handling, deployment, R&D. Obviously, all of this is related to the fact that it has enough computational power, obviously optimized computational power for parallel processing, and that is actually what helps AI with HPCs. So let's see 2 use cases for at these intersections, that is AI and HPC. So actually, NVIDIA has a couple of interesting kind of demos. You can definitely try them out, because obviously they are one of the big HPC developers. So obviously they have the means for that. So simulate workflows for product designs, for example. They use it for climate and weather modeling. us for global scale scientific visualization and maximizing developer productivity. So obviously here they actually use AI along with HPC to accelerate these things. Let's just see one concrete example.
One of the first healthcare cases we worked.
That is the healthcare one. Let's see this NVIDIA one first.
As the Earth's climate changes, AI-powered weather forecasting is allowing us to more accurately predict and track severe storms, like Super Typhoon Chanthu, which caused widespread damage in Taiwan and the surrounding region in 2021. Current AI forecast models can accurately predict the track of storms, but they are limited to 25-kilometer resolution, which can miss important details. NVIDIA's CorDiff is a revolutionary new generative AI model trained on high-resolution, radar-assimilated WRF weather forecasts and Error 5 reanalysis data. Using CorDiff, extreme events like Chanthu can be super-resolved from 25-kilometer to 2-kilometer resolution, with 1,000 times the speed and 3,000 times the energy efficiency of conventional weather models. By combining the speed and accuracy of NVIDIA's weather forecasting model ForecastNet and generative AI models like CorDiff, we can explore hundreds or even thousands of kilometer-scale regional weather forecasts to provide a clear picture of the best, worst, and most likely impacts of a storm. This wealth of information can help minimize loss of life and property damage. Today, CorDiff is optimized for Taiwan, but soon, generative supersampling will be available as part of the NVIDIA Earth 2 inference service for many regions across the globe.
Now we see for healthcare.
One of the first healthcare cases we worked on was together with Delhi MC, and it was about training a very accurate AI radiologist. Started with analyzing a dataset called the Chest X-ray 14 that was released by the National Institute of Health here in the United States. The collection contains about 112,000 X-ray images. And it's an interesting problem because this is a multi-label classification problem. So it's unlike most image classification problems that have either a single object or in an image that you need to recognize, like a cat or a dog or something like that. In this case, 1, 2, or more diseases, up to 14 different diseases are contained in this data set. So this makes the problem a bit more challenging. We trained the network on the Zenith cluster on ImageNet. We took the pre-trained model and fine-tuned it on this chest X-ray dataset. So using 256 compute nodes from Zenith, CPU-based, no GPU involved, we managed to outperform this original method from Stanford in only 8.8 minutes. We realized that you can indeed trade off memory consumption and computing time for accuracy. And that was what we wanted to prove. We decided to work with Dell EMC, HPC, and AI Innovation Lab as they proved to be very good practitioners. They had access to state-of-the-art hardware. So, and also they were working together with Intel. Since we were also together with Intel, we decided to have a joint collaboration so that we can achieve greater goals.
Okay. So in conclusion, we can say that HPC provides the power and AI provides the intelligence, and their synergy actually unlocks the unprecedented capabilities across both science and industry. So it's actually not a matter of HPC or AI, but HPC and AI, because each one of them actually accelerates the other in its own way. That's it from my side. If you have any questions, please go ahead. Oh, I can't hear you. Safa, I can't hear you. I'm not sure why.
You can.
Yes, I hear you now.
I can. Okay, perfect. Yeah, I was just saying that it's really interesting the fact that you went from HPC to AI and then also from AI to HPC, because as you mentioned, I think the main conclusion is HPC and AI. That's the thing. So there is actually 2 questions from the audience. So someone is asking, will the presentation be shared later? I mean, it was actually extremely interesting, so I don't blame them for asking.
Sure, if you want it, sure, I can share the PDF format of it for sure.
Okay. Perfect. So actually, the webinar will be on YouTube. So if you look for it later, I mean, just after we're done, you're going to find it on YouTube. So then you can find all the information that was shared, in addition to Sarah's comments on it. But yeah, if you need the slides, you can just maybe send us a message on our page on LinkedIn, and then we can provide the slides. Okay, another question. So I'm going to show it here so that we can all read it. How do you see traditional simulation workflows evolving towards hybrid AI plus simulation pipelines?
Okay. Simulation workflows evolve. Okay. All right. So actually, like as I actually like thought about so far, what we're going to see for sure, I mean, because because HPC and AI is actually less expensive that quantum computation, right? Quantum computation is still too expensive for everyone. So actually, what we're going to see is most likely like what you have seen, for example, with the NVIDIA example, right? So actually, that they're going to start to do is like kind of like try to train now AI using HPCs. They will stop using the typical cloud instances, right? And then try to figure out how to get real kind of like, let's say, for example, anything that is related to huge amounts of data, like big data, or anything that is related to climate change, anything actually that will really consume a lot of power, will be obviously used using HPC directly. And then obviously there will be power in, let's say, for example, if we have visualization model, if you have kind of like a model that is really acting on these data sets, they will be actually kind of like training it on these HPCs. So everything will be like HPC plus AI, with obviously HPC kind of like AI trying to improve all of the HPC workflows to accelerate them. And obviously AI like being accelerated in its inference and obviously even in its training using HPCs, because it's actually the least expensive approach. And even like today's, to be honest, if you actually look at a huge European, I'm not sure about the US, but when it comes to Europe, they have a lot of kind of like research labs really focusing on training HPC, especially AI specialists, to work with HPC and teach them how to best leverage HPCs. Because to be honest, we kind of like, we're never exactly were excited with kind of like learning how to deal with HPCs, simply because before they were using 100% like just CPUs. So it's only like recently that they are including GPUs inside them. So it's actually now it's much more beneficial than before. So yes, now everyone is trying to train AI kind of like experts to learn how to use HPC. Obviously, also teach HPC people how to collaborate with AI people so that they can accelerate their processes as well.
Yeah, that's actually very interesting because that was one of our
Safa, once again, I lost you.
no.
No, I think I'm not sure. Is it? Can you try getting closer? Try that.
Now better?
Yeah.
Okay. Yeah, I was gonna say that. So, in the majority of the cases, a lot of people they're just talking about AI. So AI, but then they don't know that what's underneath is actually HPC. So it's actually enabled by
Yeah.
HPC. So yeah, you need to be aware that if you talk about a large model or any model actually, then you actually need HPC, you know, in the underneath layer of whatever results you get.
Yeah, actually, like as I told you, for example, for satellite imagery, anything actually related to kind of like space, because there is lots of actual space actually research going on, especially in the
Yeah.
AI. They try to accelerate, obviously, all of the inference. Let's say, for example, the meteor, especially when it comes to disasters, because I'm not sure if you know this, but we will be having lots of disasters as we are moving on because of the climate changes.
Yeah.
I mean, it's a foregone solution, right? So we need to kind of like predict when it's going to happen eventually. So AI is going to be kind of like accelerating all of these calculations that we're usually doing, we did before in a kind of like traditional way. Now AI is going to be accelerating these calculations. Obviously, all of these calculations are already done using HPC,
Yeah.
right? They're 100 and 1000% using HPC because they are the only ones that can handle all of this information.
Right.
And AI is going to be used to accelerate them. And because like scientists have seen, as we have seen with the medical use case, they have seen how powerful HPC, like they have gone to 8.8 minutes. Do you even understand what it means? 8.8 minutes to train a model? That's impossible. Like just one simple model takes 1 hour. just to tell you the difference between an image that has a disease and an image that doesn't have a disease, right? And
That's
it's only
revolutionary.
handling, it's only handling like how many 6,000 images, and it takes 1 hour and something, right? But they actually have handled 112,000 images in 8.8 minutes. That's not just incredible, that's amazingly kind of like a dream for us. So
Yeah.
it is really accelerating the process of actually training AI models. And with LLMs, kind of like consuming so much power,
Yeah,
for
pretty much
sure
the
they
same.
will be like, everyone will be moving to HPCs, like, kind of like trying to understand how to make them more so we can get things accelerated.
Yeah, that makes sense. Yeah, so they're saying thanks a lot. It's interesting. I see.
I have a
Dr. Ahmed?
question,
Yeah.
Safa. Yes, thank you, Safa, and thank you, Dr. Al-Atif, for the excellent presentation. It was very informative. So you raised a very important point about the energy optimization in HPC using intelligent resource scheduling. So I'm trying with my colleague Robert to work on this stuff, but it's like a bit difficult. We having a different workloads and stuff like that. So, from your point of view, how does such AI enhanced scheduler perform in real world applications or workloads compared to what we have now with Slurm with default heuristics?
Yeah, actually, like if you remember, like what does AI do by the end of it, right? Like how do we even train AI? So we kind of like use its use cases, right? The different use cases that you have seen. So you collect. So you might already be having logs around. I don't know, like the different kind of like resources that your current HPC is using. When is it using them? When do you need these resources exactly? And which type of resources you're using at which type of time, right? So actually what AI does is take all of this in and kind of like, it's like what we humans do. Like I see that, let's say, for example, I see that in one January, like for example, one January, always in one January, there is a high spike for demand for this type of rack, right? So it's going to just like, tell you like, instead of using this kind of racks, directly go to these racks. You do not need to travel all of these ways just to get to this kind of like performance. You need to only simply use this rack because it is actually the one that kind of accelerates all of your processes. So it's kind of like learning from your own experience already, because you have already used your HPC so many times. So it's going to take all of this data and kind of like tell you the best decision. For this type of calculation, you only need these kind of laptops, because usually, obviously, it might also actually go deeply into improving your own code. So say, for example, your code actually right now, if you run it, it might take actually 10 hours. But if AI actually gets to optimize your code, it might actually take like 5 hours. It might reduce all this time, and then obviously kind of like choose the best resources to use based obviously on the knowledge you will be actually teaching it, obviously based on all the experience that you have. This is like really what is the power of it. It learns from your own experience, let's call it, obviously from the experience of the different people that have been using that HPC, to know when to leverage a certain resource and exactly when, how, and obviously to optimize if when it comes to code or even communications, as you know, because sometimes what we do is like, even just humans, like so kind of like sometimes it is nearby, we actually have to go here. So AI might actually tell you, here is a shortcut, instead of you having to actually go through all of this.
No, but actually, we need to go through all the codes and platforms, yeah, so on and so forth. No, because what we aim at the end, it's to maybe optimize the resources that
Yes.
in the jobs. No, right? Not only choosing the right nodes, because at the end we somehow use the InfiniBand, and we got, yes, we don't see the like latency between using like not only close nodes or something like that. But yeah, well, we are trying. So it's maybe, yeah, I can help, but it's a bit difficult, because we need also to have access to all the Slurm files, different like understand different tools, and so on and so forth, right?
Yeah, actually, like, to be honest, if you want it to be optimized, like for your use case, right, you need to actually have already done it by yourself. You need to have lots of experience with your actual HPC. Actually, might even be only beneficial if you have already gone through, I don't know, a couple of years, let's say 10 years, you have been using it for different use cases that you might have to be using it for. And then it will learn based on these actual experiences that you yourself have had so far to actually make the best decisions for you. So I do not think it will be very helpful if it's your first, kind of like if it's your first
No,
year.
it's not my first time. I'm like using HPC since
No, not you. I'm talking
yes,
like
yes.
if you have gathered
Yeah.
enough information
But
from your
yes,
own experience.
still for me it's not. I'm not I'm not. I don't use all like the tools. Maybe some tools in simulation some tools in training and so on and so forth. But yes, even if we work like for many years, we cannot cover all the.
That's for sure.
Yes.
That's for
Yeah.
sure.
No,
So
But
for example, you can train it using just currently what you know. Just if you have it, you can gather all of your data, kind of like the code that you're used to run, right? It will be great if you can have some diversification, if you can figure out if there is a way to optimize the code that you're working with, right? Let's say, for example, you have code version A, code version B, and code version 3. Please make sure that you have the worst also programmed, so it knows you kind of like the different use cases, so it can actually learn what is really best to choose when and how. Kind of like you need to have as many use cases as possible.
So what we are trying now, it's so we are trying to work with some LLMs to enhance HPC support, like for native users, maybe generate some kind of file jobs or something like that.
Oh,
So I
I
think
actually wouldn't
it's
recommend using LLMs, to be honest. Actually, I believe like the best thing you can use in this kind of like optimization is to use kind of like traditional AI-based algorithms, or the ones based on traditional AI algorithm. That is either symbiotic AI or actually use things like reinforcement learning, because it is based on symbiotic AI, right? Or any kind of like game theory-based algorithms. The new algorithms aren't really good at optimizing resources, if you ask me, because they do not have the right kind of like calculate, kind of like the logic behind it is not really as strong as the traditional AI ones.
yeah, of course, yes. So, but with the
yes, they were
reinforcement
built
learning,
to
we need
learn.
to go through the codes and like make some modifications and yeah, you know. And sometimes it's difficult to do these modifications inside the cluster who is working. So maybe it can modify all the scheduling part and some stuff like that.
Maybe you can, why don't you just run an experiment on a small set of the cluster? It's best to go on a small set, even if you have to just choose like one specific set from the HPC, right? That perhaps like mostly isn't used all the time, and just run an experiment, right? You can even just
Yes,
run a machine, right? Just because you want to just get the gist of it, because if you can run one, you can run 1,000. But if you can't run one, a simple one, obviously it will be very hard to run the thousands.
Others.
yes, of course. Thank you. Thank you.
We have another question from the audience. Which tools or frameworks would you recommend for managing massive parallelism in AI training? Is it the same, PyTorch, TensorFlow, etc.?
Usually, actually, for training AI models, we do use, well, the most optimized, obviously, might be, to be honest, like this is the following. We usually use, when it comes to actually optimization, JAX. So Google JAX and FAX are actually the best when it comes to optimization, because they're actually kind of like directly talk to the machine. But PyTorch is good as well, definitely. So you can try PyTorch. But to be honest, like when we really want something accelerated, we get PyTorch and then we load it and then we code everything into C++.
Okay.
So you kind of like need kind of like frameworks and tools that directly speak to the machine. So it is best to use JAX. That's actually the best when it comes to parallel computing for now. PyTorch has also been optimized for it, but obviously it is slower than JAX and FAX. So yeah, you just need kind of like any tool that can speak directly to the machine is 1,000 times much better than using the current frameworks, for sure. If you want to accelerate, obviously, training.
Okay. I hope this answered your question. Okay, so we have Jisam Hussein. Thank you very much for this insightful presentation.
You're welcome.
I have a quick question just before we wrap up. So when you talked about AI for managing resources, so this kind of joins Zaimet's question about the like the resource management and eventually the energy also consumption management or just prediction. So so how I imagine it actually is that okay, so you have your jobs that are running, and then you take, for example, it's not measurements, but you just log the, you know, the resources that are being used by your jobs in points of time, right? And then you use, so as you said, you need to have a lot of experience with it because you need to know exactly what's happening. And you need also to have your logs ready because you need that data.
Actually, even for the metrics, for example, for if you ever checked out research papers when it comes to AI, we actually have a metric that is called flop. But very few people actually know what flop is. Because no one actually deals with the actual computation power, right? But this is a specific metric that really shows if an actual model is truly time-saving or not. So any paper that doesn't have a flop in it, it means they have no idea what it means an AI is actually trained in less time than
it's not useful.
You need the right metrics, and this is actually the tricky part, because you really need to understand kind of like not just kind of like what HPC is and how it works, but you really know, let's say, for example, I'm just going to show something. Let's say a Mac, right? Might have like GPU of Mac, as you know, M1 or M2. They're different, right? M1 metrics are not M2 metrics because they have different hardware, different components. So if you have a deeper understanding of the components and their compositions, actually it is much more efficient. You'll be able to push much more harder. You can even get this information, right? You do not even need to kind of like, even you do not even need to get as much data as you might think. You might just give in, like, for example, the LLMs, you can just give them as context. The kind of like, I know that I have, I don't know, let's say I know that I have M1 chips in my HPC, right? For GPUs, I'm just throwing something like this, right? So I know, based obviously on the manufacturer, that for M1s, like for example, for work, for I don't know, let's say a parallel job might take me 10 seconds, right? Depending on parameter X, Y. So you can just give all of this into context, and then obviously the AI will calculate, let's say, for example, your code, how much it would run, for example, based on these parameters, and it would know what to optimize with it, right? So if you actually have a deeper understanding of the components that you have in your HPC, it's obviously you'll be able to optimize them much better. If you also understand, let's say, for example, I'm not sure if you know this, but also the climate plays a huge role, right? So cooling is a big issue, right? And obviously, if you know, let's say, for example, in places that we have high heat, your actual system might slow down. Like even for example, laptops, all the laptops that we have right now, they're not optimized for Middle Eastern actually weather. They're optimized for European and US weather, which are actually extremely cold, and usually when they have some kind of climate, so usually less heated than ours. But it's normal. But we buy them. We need to deal with whatever is happening. So actually, the lifetime might actually be reduced. So if for them, for example, it takes 10 years for the laptop to crash, for us it might take 5 years to crash, right? And perhaps it might go slower in summer than in the winter. So all of these factors actually kind of like impact the actual resources. You know, everything is like a human being. Like as we get affected by everything gets affected.
That's true. Yeah, as you said, there are a lot of things that we need to put into the equation so that we can have like an actual result that we can act on.
That's true. That's why usually like you need experts, I guess. That's why actually, like I told you, like that's why right now they're trying to train AI people into HPC and HPC into AI. So they kind of like how to best kind of like power up these things so we can get the best of both.
Because they actually go hand in hand. I mean, this is a fact. So we just need to deal with this fact.
Actually, like even for cloud resources, not sure if you know this, but usually Actually, most cloud providers are using AI currently to actually power up all of their kind of like servers and obviously
Yeah.
power, kind of like data warehouse and all of that. They use AI 1000% to handle everything from scheduling
Yeah.
to actual heating, cooling, whatever you think about it. They're using AI to get
There's
rid of that headache.
yeah. All right, perfect. Thank you very much, Dr. Sarah. It was really, really a pleasure to listen to your talk. It was really interesting how you mix all the concepts and all the components. It was actually amazing. And I really appreciate the time that you gave to this presentation and the time that you gave us to deliver the presentation. I do really appreciate it. I know that you have a heavy schedule and yeah, I do really appreciate it. Thank you very much again.
You're welcome. It was my pleasure. Thank you for inviting me as well. I hope it was a fruitful session.
Yeah, it was
Yes,
amazing.
yes,
Yeah.
it was amazing. Thank you very much.
Thank you, everyone.
Thank you.
Salam
And
alaikum.
as I mentioned, the webinar will still be on YouTube, so maybe someone will reach out to you to ask
Yeah,
to
sure.
yeah, to clarify things. So yeah, so it will
Please
be
go
on
ahead.
YouTube
Reach out to me
available.
whenever via my social media. Usually I'm more active on LinkedIn, but feel free to
Perfect.
send me wherever.
Okay, sounds great. Thank you very much again, and have a great weekend, everybody.
Yeah. See you all.
Bye. Bye.